Welcome to Calc Chats 30. Today we're going to be diving into power series, and we're going to be talking about how to find them and how to use them. We're going to take it back to our geometric series. So in Algebra 2, we learned that the sum from n equals 1 to infinity of a times r to the n minus 1, that sum is equal to a over 1 minus r, so long as the absolute value of r is less than 1. Or I'm going to rewrite this just for our future series. R is between -1 and 1. So this is just geometric series. If r is less than absolute value of r is less than 1, that we know this sum works. And so in calculus, we don't always deal with this series exactly. But I'm going to let a equals 1 and, r equal x. And so rewriting the series, n equals 1 to infinity of 1 times x to the n minus 1, this sum is equal to 1 over 1 minus x. So all I did here was change r into 1 or a into 1 and r into x, and to get this series. And this is basically what we call our power series. So we're not dealing with r is equal to a number. We're dealing with the variable x in this power series. So real quick, what I'm going to do is, this is kind of a form of the power series, but we mostly see it in the form n equals 0 to infinity of x sub n. So instead of n minus 1, where n equals 1, we'll get x to the 0. This is just n equals 0, and that way we're starting off x to the 0. So writing out the terms of this polynomial, we get x to the 0 plus x squared plus x cubed plus x to the 4th plus all this. So this is a sum of our polynomials. So it's not a function, it's actually a series of all these polynomials, and I'm adding them up. And there are a lot of things that I can do with power series, and they're going to kind of lead us into Taylor and Maclaurin series eventually. But basically what we can do with this basic power series is we can differentiate, integrate, we can find the radius of convergence, we can create other power series from this singular power series. So it has a lot of, pun intended, power when we're talking about series and the power series. So this is a type of problem that you might see when we're using power series. So it asks you to find a power series that represents 1 over 1 plus x on -1 to 1. And this is what we will learn to call the interval of convergence. And again, this just kind of refers back to that r is less than 1. So from -1 to 1, that's our interval of convergence. So looking at this series, the only series I know is 1 minus x, and I know that's equal to the sum n equals 0 to infinity of x to the n. So when I'm looking at 1 over 1 plus x, I need to be able to rewrite it to get it back to kind of in terms of 1 over 1 minus x. So if I rewrite this series, I can take 1 minus -x. And so in our first scenario, I was plugging in positive x. In this scenario where I'm trying to make the new power series, I'm going to plug in -x. So this is the same as saying -x to the nth power. Another way of writing this is the sum from n equals infinity, n equals 0 to infinity, -1 to the n, x to the n. Because if I split this up, I'm taking -1 to the n and x to the n. So either way, both of those series work out. And if we kind of start writing the first couple terms at n equals 0, we just get 1. And then n equals 1, when we plug this in, we should get negative x plus x squared minus x cubed plus x to the 4th minus x to the 5th. So this is very similar to our other series, only this is an alternating series. So this is one example of a way that we can construct a new power series just from the one that we know about right now. So here's a DIY problem for you to try. Try to find a power series that represents x over 1 plus x on the interval from -1 to 1. So same thing as we did this slide before. I'm going to pause it, try it yourself, and then check your answer, see if you got the right solution. So you should get that the series x over 1 plus x can be represented by the series from n equals, the sum from n equals 0 to infinity of -1 to the nth power times x to the n plus 1. So basically, we kind of can split this up. We already know that this series is -1 to the xn, -1 to the n times x to the n, and we multiply that series all by x, and so you can kind of see we infinitely distribute, but then this ends up being -1 to the n times x to the n plus 1. You can do it this way, or you can just kind of distribute it into the series in the original form. Here we're asked a little bit of a different question. We're asked to find the power series to represent 1 over the entire quantity 1 minus x squared. So we haven't really dealt with this yet, but if we notice, the derivative of 1 over 1 minus x is actually equal to 1 minus x squared. And so here we can kind of deduce that if I take, there we go, if I take the derivative of this series, n equals 0 to infinity of 1 over 1 minus x, I will get 1 minus x squared. And so if we look, I'm so sorry, this should not be 1 minus x, this should be x to the n, which represents 1 minus x. So if we look kind of at the terms of the series, we just want to basically take each term. So we get 1 plus x squared plus x cubed plus blah, blah, blah. And when I take the derivative of that, I get the derivative of 1 is 0. So I get 1 plus 2x plus 3x squared plus 4x cubed, and it keeps going down. And I can also see, if I look at my original series, x to the n power, the derivative of this, I didn't even have to do term by term differentiation. The derivative is just n times x to the n minus 1. And so this is equal to 1 over 1 minus x all squared. So we can take derivatives, we can take integrals, and we can do it term by term, or we can just look at the series as a whole and take the derivative of whatever power series we're looking at. The last thing I want to touch on is what we call the interval of convergence, and with that, kind of the radius of convergence. So here we're given a power series, and we know it's a power series because we have a variable in for x. Normally, we would look at this, and if we had a number in for x, we would try to do some limit comparison test. We would try to do something to figure out if it converged. But since it has the x in, we have to use a different method in order to find for what values of x this will converge. And so we use the ratio test for our interval and for our radius of convergence. So if we remember, we take the limit as n goes to infinity of our a n plus 1 over our a n. We need that absolute value. So a n plus 1 looks like n plus 1, x to the n plus 1, all over 10 to the n plus 1. And we can divide or multiply by the reciprocal of just the regular sequence. So now when I'm taking this limit, and then goes to infinity, first thing I really want to do is I want to try to get my x's out. So when I'm canceling things out, I can cancel out the 10 to the n. I can cancel out the x to the n. But I'm left with a single x here. So I'm actually going to take that and kind of separate that from the rest of my limit. And so I'm left with n plus 1, and then all over 10n, because I still have that 10, and there's the n. So now the limit as n approaches infinity of this ends up being the absolute value of x times this limit goes to 1/10. And so going back, we remember that our series converges if the absolute value of r is less than 1. And so in order to find the interval of convergence, I take this less than 1. So now I can multiply both sides by 10, so I get that the absolute value is less than 10, which means that my interval of convergence is from -10 to 10. So what this means is as long as x is between -10 and 10, the series will converge. And if I go back up and I look at where x is, if x was equal to, let's say, 9, this looks like a geometric series, and this would converge because our r is less than 1. And so this interval helps us determine for what values certain power series are going to converge, even when they look tricky. So our interval of convergence is 10, and when we look at our radius of convergence, we know that x can go 10 in either direction, so our radius of convergence is equal to 10. So here are your ABC problems to try. Please notice that they are slightly different problems, so each of them is requiring a different technique. And so the first one, we're finding a power, well, the first two, we're finding a power series that represents, for A, 1 over 1 plus 3x, and for B, ln of 1 plus x. And for C, you're asked to find the interval of convergence of this problem. So just because you can't get A and B doesn't mean you necessarily can't get B. And again, just because you can get C doesn't necessarily mean that you get A or B. And so please try them all. Come to the class with any questions that you have. And thanks for watching, and please like and subscribe. Just kidding, I just forgot to put in the answers. So I'm going to go ahead and pause the video real quick and then get you your answers before we end this video. So here are the answers. The first one is the sum from n equals 0 to infinity of -3 to the n times x to the n, or another way you could write this is just -3 x to the n. Part B, we should get the sum from n equals 0 to infinity, -1 to the n times x to the n plus 1, all over n plus 1. And then the radius of convergence is 10, but your interval of convergence is from -8 to 12. So these are the answers. Again, I'm repeating myself. Please like and subscribe. Make sure to ask, bring questions to class, and thank you for watching.